So welcome everyone. Today our speaker is Uri. Uri is a fourth-year PhD student at Tel-Aviv University. He's advised by Yishay Mansour and Tomer Koren. And prior to that, Uri spent a few years in various engineering and management positions. And before that, he obtained his bachelor's in Tel Aviv and his master's at the Weizmann Institute of Science. And his research interests are in stochastic optimization and RL. And the co-host today will be Gergely, and I guess you can get started, Uri.
Okay. So hi guys, and thank you very much for the introduction. So I'm going to tell you today about our recent paper titled Rate Optimal Policy Optimization for Linear Markov Decision Processes. And this is joint work with Alon Cohen and my PhD advisors, Tomer Koren and Yishay Mansour. So this indeed, of course, is a talk about reinforcement learning and more specifically about a theoretical model of reinforcement learning, which tries to go further in modeling real-world complex environments. And to put it more accurately, while in tabular methods, we look for algorithms that have computational and statistical complexity that scale with the number of states. In the function approximation setup, we're looking for complexity that it scales with some inherent complexity measure of the environment, but not the actual number of states. And in this work, as can be guessed from the title, we're looking in the linear MDP model, which arguably is the standard for today of linear function approximation in reinforcement learning that was proposed and popularized by the influential work of Jean et al. From 2020. So the gaps in theory of linear MDPs, which we try to address in the paper, is first doing online reinforcement learning, that is regret minimization with non-stochastic losses. This is motivated by trying to learn more in a more complex setup, relaxing IID assumptions, and by the fact that in the stochastic case, we do have online guarantees that are optimal. And the other motivation is in the study of policy optimization methods, which I suppose all of you are familiar with. But in short, these are methods that update the policy parameters to try to optimize the value induced by the policy. And this class of methods is extensively used in practice, but even in the most basic setup of stochastic losses, the sample complexity we could prove in theory was suboptimal compared to what you can do with value-based methods. So in a bit more detail, if we're looking at the classic sample complexity setup of stochastic losses and bandit feedback, to get to an epsilon optimal policy, the work of Jean et al. Already showed how to, using UCB LSVI, using 1 over epsilon squared episodes of interaction to get to an epsilon optimal policy, while policy optimization-based methods, such as those that were the state-of-the-art prior to our work of Zanetti et al. And Liu et al., which actually also presented here not too long ago in this seminar, got to a suboptimal 1 over epsilon to the power of 3. And then looking into the online case with adversarial losses and full feedback. So sorry, I don't remember if I mentioned, but of course, bandit feedback means that the agent during learning observes losses only along the state actions she has visited, and full feedback means she observes the entire loss function after each episode. So the recent paper by Zong and Zhang showed a variant of the natural policy gradient that achieves the regret of k to the power of 3 over 4. And then this is not the setup we're going to talk about today, but just to complete the picture, if we're looking into online guarantees with adversarial losses and bandit feedback, then we have the work of Liu et al. Also recent work. It's not the same Liu of the sample complexity setup. So they actually give a rate optimal algorithm that is not policy optimization based, but it is also not a polytime algorithm. It is not computationally efficient. And they give an algorithm that is policy optimization, but not based on exponential weights, that also achieves the same regret of Zong and Zhang of k to the power of 3 over 4. Now, of course, just to say the obvious, the bottom line can be used in the middle one, and a policy optimization algorithm, of course, can be used as any algorithm. So as mentioned, our talk today is about policy optimization, and our main result is a policy optimization algorithm that obtains the optimal online guarantee of square root k, regret. Optimal, that is, with respect to the number of interaction episodes, for both adversarial losses with full feedback and stochastic losses with bandit feedback. And as a simple corollary, which follows by a standard online to-batch conversion, we also get the rate optimal sample complexity in the stochastic losses bandit feedback case, of course. In the talk today, I'm going to focus only on the adversarial full feedback case, just to keep things simpler, but the differences between the two setups in the algorithm or in the analysis are minor. Okay, so let's go through some preliminaries. So we
so maybe before that, could I ask a question regarding this table that you were showing here, where you were talking quite a bit about like the distinction between policy optimization based methods and other style methods and non-NPG methods. So there was a question here in the chat, and that's also a question that I typically have when this topic comes up. So like, why are these policy optimization methods of specific interest? Are they really all that different from value-based algorithms as they are being analyzed, or why do they require such special attention?
So that's a good question. First, I can say in terms of when we try to tackle, to say the obvious, when we try to tackle non-stochastic settings, then basically the policy optimization-based methods that are use variants of mirror descent are the methods we know how to use to obtain online guarantees for non-stochastic losses. But apart from that, I guess my answer would be like, why study the sample complexity in the stochastic case? That's a real question. And I think the way I see it, they do, they as I said in the previous slide, these are methods that are, of course, have variants that are used in practice. So I guess to justify it, it's to say that we're trying to understand better an algorithmic approach that can have some bearing on things we do in practice.
Yeah. I guess I have some potentially controversial questions about that. Like, I guess when you say that these are being used in practice, then what is it that this precisely means? Is it that you use softmax parameterization in practice, but then you don't necessarily feed them with like just unbiased Q function estimates? Maybe something else.
But that's true. It's true. The policy optimization algorithms we use, if you think about actor critic methods, that they maintain a model to estimate the Q function instead of like if we're looking like what we do here with linear NDPs, instead of learning the Q function applying gradient descent, we learn it with backward dynamic programming and least squares regression. But if you look from a high enough level, it is doing the same thing, only we're learning the Q function in a closed form way because we have this assumption on the environment. And I can also mention there have been a few works from the very recent years that take it a step further in looking into true policy gradient methods and learn the Q function with like this, I think it's called 2-time scale or something, where they're alternating between gradients to learn the Q function and gradients to learn to optimize the policy with respect to the Q function. So you can view what we're doing here with linear MDPs like just one step before that, okay? Because it's correct that the 2-time scale framework models more accurately, true algorithms, also with some, this is also not completely true. And what we're doing here is also doing that, but maybe just to a lesser extent.
Right. Yeah. I think, well, we could talk about this for quite a bit longer, but I think that this is not the point of your talk anyway, so I'm not going to like
okay. Yeah,
much more of your time on this. So let's just go ahead with the content, and maybe let's return to this later. But thank you for the answer.
Okay. So let's quickly go through some notation, which is fairly standard. So we denote the Markov decision process by capital M, and it is a tuple of the state space set, the action set. We think here about the state space as either infinite or just very large, the action set as finite. And the horizon, this is an episodic Markov decision process, finite horizon, which each episode of interaction continues over capital H steps. Then the time inhomogeneous dynamics, that depends on the time step, and the sequence of capital H losses, and the start state, which we assume here to be a constant without loss of generality. We denote the policy of the agent acting in the MDP by pi, which is just a mapping from states to probabilities over actions. And a single step of interaction in the MDP proceeds in the standard way. And in the online adversarial episodic setting, we consider capital K episodes of interaction, where in episode K, the agent interacts with the MDP M superscript K, which shares all elements with the rest of the MDPs from the rest of the episodes, only with a different loss function that is denoted L superscript K. And because this is an adversarial setting, we're not making any assumptions about the loss functions. They're not coming from any distribution or something like that. And value and action value functions are, again, defined in the standard way, only that they have this extra superscript K that denotes which episode of interaction they belong to, they relate to. And the main structural assumption, of course, is that all these MDPs are linear in the sense that there exists these known feature embeddings phi that take the state action pairs to d-dimensional space, and unknown signed measures psi that take the next state, so to speak, to the same d-dimensional space. And if we think about the dynamics in the finite state space as a transition matrix, then it basically means that this transition matrix is low rank decomposable with these feature embedding matrices. And also the immediate loss function is also linear in the same 5 features, in the sense that we have this low dimensional cost vector or a sequence of capital H of them, such that the loss in any SA is phi SA times this inner product with this low dimensional cost vector. There are also some normalization assumptions, which I'm not going to go into, as the level of detail in this talk is not going to necessitate them. So to summarize the problem setup, the interaction protocol is such that the adversary or nature chooses these sequence of K low dimensional cost vectors. And then we have a capital K episodes of interaction where the agent in each episode K, the agent chooses a policy, plays it in the MDP, the linear MDP, which is induced by the low dimensional cost vector that was chosen by nature. And then we observe full feedback, that is, we observe the low dimensional cost vector and proceed to the next episode. And the objective is to minimize the regret of the agent, which is measured by the sum of expected losses given by the value functions measured from the third state, minus the sum of expected losses of the best policy we could have chosen in hindsight, with full knowledge of the environment dynamics, loss functions, and so on. So that summarizes the problem setup. If there are any questions relating to this. Okay. So I will proceed now with a short discussion about policy optimization in linear MDPs in general, which starts, of course, with policy optimization in tabular MDPs with known dynamics, which is the easiest setup we can think of. So basically, policy optimization means that, or this version of policy optimization means that in each episode, we perform backward dynamic programming to compute the Q function accurately here, because we have the exact dynamics. And then we perform a mirror descent step, exponential weights. To be more precise, this is mirror descent with negative entropy regularization from each state on the actions. And it is also worth mentioning that this connection was made in several papers from the recent years, that this is in fact just the natural policy gradient that was introduced first by Kakada in 2001, or equivalent to. Okay, so now for the rest of this discussion, I'm going to focus on the policy evaluation step of this algorithm. So focusing on it. Also, please note that I use this notation of when I'm talking about the expected next state value conditioned on some state action, I'm thinking about taking if I think about the dynamics as a transition matrix, then I multiply it by the value function vector. So I get a new vector that is now in the space SA. Okay, so this is basically just another way to spell out that I'm taking an expectation on the value function condition at the next state condition on some state action. Okay, so now what changes when we move to the unknown dynamics case? This was presented in a work by Shani et al. From 2020. So they proposed this natural version of policy optimization, which they termed optimistic policy optimization. So here the optimistic policy evaluation step is basically the same as it was before, only that we have these two changes. So first, of course, we don't have the dynamics. So instead, we have an estimate of the dynamics, which is just going to be estimated pointwise. Okay, so we are just basically estimating the actual transition matrix by the empirical transitions we observed during learning. And then we subtract UCB bonus or Hofding bonus to counteract the uncertainty in the estimation. And the goal of this is just to make sure that the expected conditioned on any SA with high probability, the estimated expected next state value is going to be an underestimate of the true value. Yeah, I think that's it for this. And what happens now when we move to the linear MDP case? So we get a few more changes. So first, if we're looking at how we estimate the expected next state value, so we are no longer really estimating the transition matrix pointwise, but rather we're going to perform least squares regression to estimate the expected next state value. And the reason why this is a reasonable thing to do is because one of the most important properties of linear MDPs is that the expected next state value, if we think, for example, for 1 second about this v tilde h+1 as a fixed function, then the expected next state value is just a linear function in the same 5 features with the low dimensional vector given by this integral. That's basically, we have the value function weighting the psi vectors. So given this, as mentioned, the reasonable thing to do is to do least squares regression to estimate this quantity. And accordingly, we, instead of using a UCB bonus or Hofding bonus, we use an elliptical bonus to counteract the uncertainty of the least squares regression procedure. Just to remind everyone, we're subtracting the bonus because I'm working with losses here. So to get an optimistic estimate, we're subtracting the bonus. Another important modification in this procedure, by the way, this is just basically all the papers you see below that did studies on value-based policy optimization, pretty much did simple variants of this procedure. And all of them, except for our current paper, use this clipping operation, which to explain first why we need it, I'm going to make a small detour and first discuss how we get basic least squares concentration result in linear MDPs. So our goal is, when we're going to be in the analysis, we want to bound how large can be the error, given some state action, how large can be the error of the expected next state value we computed when doing the least squares regression. So we use the fact, of course, that this is a linear function and we are using regression to estimate it. And we would like to use the concentrations of self-normalized processes theorem by Abbasi and Yadkori et al., which is kind of just a version of least squares concentration that you can apply in a Martigan setting. But the problem with just doing this without making an extra argument is as follows. So if we look at the data set we are using to perform this regression, then if we're just looking at the state actions and next states, it's kind of built in a way that, figuratively speaking, has the right dependence structure, in the sense that, of course, when we're conditioning on some state action, we get the first sample of the next state. And then when also again, figuratively speaking, the dependence goes from the past into the future. To make this more accurate, if we take some fixed function and try to estimate the expected next state, the expected function applied to the next state, then if we are conditioning on the entire past up to some point, then we get that the error, the deviation, sorry, of the value of f applied to the next state from its mean is conditionally sub-Gaussian, which this is precisely what we need to apply concentration of self-normalized processes. But the problem is, in our setting, we're not doing this to some fixed function. We're using the value function estimate from the previous backward dynamic programming step. And the problem is that this value function estimate actually already used this entire data set, but one step into the future of the horizon. So it used state actions that started from step h+1. But this still means that there is an indirect dependence between future state actions to this value function as a random variable. So the solution, which was already present in the work of Jin et al., was to argue for uniform convergence over the class of all estimated value functions that the algorithm could encounter during its learning, which essentially brings us back to the case, to the situation where these estimated value functions are fixed and not random variables. Okay, so now I hope I convinced you that on how and why we need uniform convergence to achieve this basic concentration result. And to discuss clipping, let's look into the actual bound this concentration result gives us. And the problem comes from the fact that the bound, unsurprisingly, depends on the scale, or on the sup norm, to be more exact, of the estimated value function, which is which induces the target variable of the regression. So if we are not clipping, we need to say something about the magnitude, about the sup norm. So because this estimated value function is coming from another regression operation, the best we can do if we're not clipping is kind of work through this inductive argument that starts from the first step, the capital H step, where we actually have, because we're in the full feedback case, we actually have the exact value function. Okay, so we know that in this step, it will be the magnitude of this estimated value function will be bounded by 1, because it's just taking expectation on the immediate loss at the time step capital H. But then if we try to take into account the fact that we perform this least squares regression to bound the magnitude of the value function, the estimated value function at step H-1, then the best we can say, if we're not able to say anything smart about the query vector phi SA related to the covariate matrix, this is the lambda KH, the best we can do is just bound this value by the sup norm of the previous step times this factor of square root 2D. But the problem is that if we continue to do this across the horizon, we are, of course, just going to get an exponential blow-up that depends on capital H. Okay, so the solution for this, which is also present in many works, is clipping the values of the Q functions to lie in some reasonable range that should contain the true value. And the nice thing is that as long as it really should contain the true value, sorry, this technique, this simple technique works just fine. Now, the issue with policy optimization and where it hurts us is as follows. So because we are performing policy optimization, we know that the policy of the agent is this softmax policy that is updated by mirror descent, which essentially depends on the sum of estimated Q functions, which now we recall are just built from the immediate low-dimensional cost vector and the estimated low-dimensional vector for the expected next state value, but clipped to lie in this reasonable range. And just note that I am ignoring the bonuses here, which of course can only complicate things. They don't make things better. I'm just ignoring the bonus term. And the problem is now that these clippings do not allow us to kind of contract this function to some low dimension or lower dimensional form. So we are basically left with order of k parameters. And this means that we basically will have a policy class that has log covering number that is linear in k, which maybe a priori wouldn't be a serious problem, but of course the problem is because here I just convince you we need to argue for uniform convergence over the class of value functions. Then we inevitably have that the bounds will scale with the log covering number of the policy class. And again, this is because, for example, unlike the work of Jean et al., here the value function is not just greedy with respect to the Q function, but it is actually taking the policy of the agent and applying it as an expectation to take expectation over the Q function estimate. So the combination of these two things mean that now we have bounds, unless we do something different, we will have bounds that scale with k, which is just leads to linear regret and a vacuous bound. So the first observation made in our work is that this is not very surprising, but if we don't clip, then we will have now that this sum of linear functions can be thought of just as one linear function with a parameter that is only d-dimensional. Okay, I just pull the phi SA feature outside of the sum. And while it has magnitude, this d-dimensional vector can have magnitude that depends on k, it won't have dimension that depends on k. And so we have that by standard arguments, the policy class now has log covering number that is logarithmic in k. And as a result, our bounds will scale with log k, even after applying the uniform concentration argument. So the second observation is that now that I hope I motivated you that we should try to remove the clipping, is that if we have even just moderately good exploration, then we don't really need the clipping anymore. So to explain this, if we look at the actual Q function estimate, again ignoring the bonus term for a second, then it is the immediate loss plus the least squares regression procedure applied on the next value function. And I can decompose it now to the error of the regression and the true next expected next state value. And I can bound each of these terms, as you can see here below. And of course, the problematic term, which we discussed before, is the error term, which scales with beta times the potential of the query vector phi SA. And the observation is that if we ensure somehow that this SA n in conjunction with the covariate matrix lambda kh points in a relatively good explored direction, one such that the potential is smaller than 1 over beta, then we can just bound this quantity by 1, for example, which will imply that the Q function estimate is bounded by the Q function estimate at SA is bounded by the sup norm of the value function estimate from the previous step plus 2. And the important thing here is that now we got to the point where instead of having something that we multiply across the horizon, we are only adding something across the horizon, which of course means that even the lowest time step value estimated value function with this constant I have here will be bounded by 2h minus 1 and not something that depends exponentially on the horizon. Okay, so at this point, we are ready. I'm ready to present the algorithm, which just takes these ideas from the previous slides and applies them. So thankfully, we have a previous work by Wagenmaker et al. That I will describe shortly that gives us a reward-free exploration algorithm that we can use here. So first to go through the steps. So we apply this reward-free warm-up procedure only for a moderate number of episodes. And then we define what we call the known state sets, ZH, exactly according to this bound on the potential of the state actions, which we know we will be needing in the analysis. Okay, so the known state set at time H is all the states such that no matter which action we take, the potential of phi SA is going to be bounded by 1 over beta when we use the covariate matrix induced by the data set returned from the reward-free warm-up procedure. And then the next simple modification is, instead of clipping the Q functions, we, so to speak, restrict them, so that we just zero them out outside of the known state set. And inside the known state set, we just take the regression and the bonus and everything and just keep it as is. Finally, just to also mention that the only modification to the actual least squares procedure is that we use, for the data set, we use the reward-free warm-up data set of step H, combined or unioned with all the triplets that we have seen since we exited the reward-free phase. And finally, I'm not going to discuss it in this talk, but to avoid having the bonuses, again, bringing us to a situation where we have a policy parameterization which is dependent on K, we put the bonuses on some schedule that we make them not to be updated not too often. A logarithmic number of steps, basically. And just to say just a few words about this reward-free warm-up algorithm, which is mostly based on the work of Wagenmaker et al. And the guarantee of this method is basically that when we give it these two parameters, epsilon coverage and beta, it will run for order of beta squared over epsilon coverage episodes, and it will return us data sets that have this coverage guarantee. And what it says is that any policy can go outside the known state set at time H with probability only that is bounded by epsilon coverage. And we get this with high probability. Okay, so the idea, I'll also show it briefly in the analysis. The idea is now that we really don't care what we're doing outside the known state sets, because any policy, in particular the benchmark policy which we are competing against, can only get there with such small probability that we don't care what's going to happen there. So in terms of the analysis, so of course the main novelty of what we do goes into this concentration bound, which is similar to the concentration bound you prove when you have clipping instead of what we did here, only that we prove it without clipping and only for the known states. Okay, so we prove that the error in the least squares estimate of the expected next state value is going to be bounded by beta times the potential without clipping, but only for the known state sets. And inside the proof of this lemma, which I'm not going to go into, we have this inductive argument that relies on the definition of the known states I gave before. So to summarize, just to give a very brief overview of the analysis, we first bound the regret over the episodes that came after the warm-up. And it goes as follows. So we use the extended value difference lemma. It should have been written here, but it's due to Shani et al. And also has a version of it in a previous paper by Kai et al., which decomposes the regret to these three sums of expectations, the bias, OMD, and optimism terms. And just a matter of notation, which I used here and didn't use before, the expectation is taken over the occupancy measure of the policies. So in one case, it will be the policy of the agent. This is mu superscript k. So this is the probability to get at time step H to state SA, condition that we use pi k. And then the same goes for mu star, but it stands for the occupancy measure of the benchmark policy pi star. So after using the extended value difference lemma, we condition on each of these expectations, we condition on the states belonging to the known state set. And after conditioning, we can just pay the maximum amount of loss on the states outside the state set, outside the known state set. And we pay a total of only epsilon coverage time, order of epsilon coverage times k for this, because we already know, due to the reward-free warm-up guarantee, that any policy, be it the agent's policy or the benchmark policy, can get to those states only with a probability that is bounded by epsilon coverage. And now we can use the guarantee, the least squares concentration guarantee I discussed in Dilemma 2 slides ago, to bound the bias and optimism terms in a standard way. So we get the sum of expectations over the potentials, which is bounded by order of square root k. And the OMD term is bounded, again, by standard arguments, because we are using a mere descent algorithm from each state to bring us to a final bound where we only need to additionally pay for the first reward-free warm-up period, which, as mentioned, we pay beta squared over epsilon coverage for it, but I just didn't put the other parameters here. Which, after choosing epsilon coverage to be 1 over square root k, we get to the optimal square root k regret bound. And yeah, if there aren't any questions, this is the end of my talk.
All right, great. Yeah, beautiful. Thank you very much. So, yeah, this is a tough problem that a lot of people have been thinking about, I think. And this solution that you found ended up pretty cool. So there was like, so maybe before I get into my deeper questions, so maybe I can just ask like a bit of a clarification there about this epsilon cov thing that you had. So the way that you said it is that the probability of seeing a state S that is outside.
Yeah, this is the guarantee.
Set is. So I'm just a little confused as to how, as to the meaning of this statement. So is it the case that the probability that you will ever see a state that is in the unknown set is small?
Yeah, exactly. It means that no matter which policy you play in the MDP, the probability of it getting to an unknown state, unknown in the sense that is written above here, that the potential is larger than 1 over beta, is smaller than this epsilon coverage parameter that was given to the algorithm.
Right, I see. Okay.
I guess it's crucial that this is a finite horizon problem, right?
Yes, I believe so. I've actually discussed it with someone not too long ago. I think, for example, the algorithm of Wagenmaker, the algorithm we use, which is based on Wagenmaker et al., uses as a subroutine an algorithm again of Wagenmaker et al. That is called covertrage, which uses this greedy policies. So this, again, I actually just learned this very recently, that in the infinite horizon case, we need, at least generally speaking, methods that use slowly moving policies. So I think even just the reward-free algorithm would not work in the infinite horizon setup, at least not as is.
Yeah, that's not necessarily the part that I would be worried about. It's more about the possibility of somehow, after playing a sequence of policies, you actually may end up in a state where no stationary policy would end up at. So like this is like outside of the initial exploratory phase.
Yeah, that's correct. I agree.
Yeah, so I guess like really what Csaba is trying to say with this is that this whole approach that you cooked up, so this seems to be like very highly specialized to the finite dimensional, or sorry, the finite horizon case, right?
Yeah, I tend to agree.
So have you thought about doing like an infinite horizon version of this? Maybe starting small and saying that, okay, I have like a reset option that I can go back to an initial state, and then trying to like optimize, for example, like a discounted return or something like that.
But wouldn't you say if we are allowed to do resets, then it's not very different from the finite horizon case, isn't it? The problem is only if we can't reset. The question is it an episodic? If it's an episodic setting, then I would assume that the discounting is not what's going to hurt me, but I haven't thought about it very much. But if it's non-episodic, then I agree. Definitely there is a problem in many places, and we haven't thought about it, to be honest.
Right. Yes.
I guess what happens in the infinite horizon case is that you don't really, I mean, there is an effective horizon. If you knew what the optimal policy is, then that would give you an idea about the span of the optimal wave function. It gives you an idea about how to approximate the infinite horizon average cost MDP with a discounted MDP. If you don't have that, then okay, you don't know this. And everything kind of hinges upon of knowing some horizon. I agree that like whether it's discounted or not shouldn't matter. If it's a discounted MDP, you still can truncate and you'll be fine, right? The effective horizon is known ahead of time. Yeah, like so the problem is not knowing the horizon is, for example, this statement here, right? Like it says that for any age, okay, any age within so many steps, but like, okay, if the number of steps is infinite, then this is not going to hold. But obviously it's going to hold. Like you can make this statement for any fixed number of steps.
Right.
You just need to run the algorithm a little bit longer. Yeah. Very cool, by the way.
Thank you.
Yeah, I guess the reason that I was not asking a million questions about your talk all the time, because of course I've read this paper like very carefully before, and I've been admiring the creativity in this trick for quite a while now, and I really appreciate the elegance of the solution. But I guess I have like a bit of a deeper question regarding like the whole like motivation of doing this kind of reward-free warm-up and all this like complicated algorithm, because I guess this is at the end of the day like this with this warm-up thingy, the whole method gets a little bit complicated.
That's true.
I guess what I'm really wondering about is
chat quickly.
Say again.
I just think maybe I can ask the question in the chat first quickly before.
Right. Yeah.
Yeah.
I guess okay. So I'm going to finish my digression after this. After we get to this question in the chat. So maybe Z, you can ask a question. You can just go ahead.
Yeah, if I can ask, just ask it.
Yeah, I have already asked this question, but you just like said a little fast, and sorry, I don't have like good listening. So I just try to summarize your answer and just check with you.
Should I look in the chat? You're saying?
Okay, okay. I can also read out. So you think that compared with value-based algorithm, policy optimization just has two advantages. One is more empirical success. The other is to update both actor and critic at a 2-time scale. Yeah, it's more accurate than to only update the critic.
Okay, so no, what I meant is first, it's not, well, I would say that the policy optimization methods, like if we think about the term from a high level, where you update policy parameters to climb a value function, just at this level of detail, then they are just, yeah, they are extensively used in practice. So as a result, they also have, I guess, maybe more empirical success, but you know, it won't even be accurate to say, if we think about, for example, Q-learning as a pure value-based method, then I think at least of a very a lot of empirical successes are due to algorithms that also incorporate policy optimization. And maybe that's how I would put it. You have many algorithms that are not just Q-learning. They also involve updating policy. That's for the first part. The second part is just that I meant, when I was discussing before, I was trying to say that I was noting that if you go in a bit more detail, the policy optimization procedure we study here, for example, it goes a bit further in describing policy optimization methods used in practice, but it doesn't go the whole way. And why it doesn't go the whole way, or at least not further along the way, is because in most policy optimization methods used in practice, specifically in actor critic methods, you learn the Q function by gradient steps and not by least squares regression closed form solutions, of course. That's what I meant, that if we want to go even a step further in trying to study an empirically used algorithm, then we would also remove the least squares regression part and exchange it with a gradient-based learning process. And then you arrive at these recent papers that studied this two-time scale framework for that also applies for actor critic algorithms. That is what I meant. I hope that's clearer now.
I think so. Yeah. Okay. Thank you.
Yeah. Right. So given all that discussion, I guess my real question at the end of the day is that okay, so is this analysis or are related analysis about these so-called policy optimization methods? So are these like really addressing like the main crucial difference between value-based and policy-based methods, or are they talking about something else at the end of the day, right? So like, do we truly believe, for example, that policy optimization-based methods are harder to analyze than value-based methods because of this discovering number issue specifically, or is there some more fundamental difference between the two that remains to be addressed somehow?
You mean from a purely theoretical point of view?
Yeah, like, well, whatever you call a purely theoretical point of view. I guess my question is like very speculative, and I'm just asking, like, making the step from a value-based method to this style of a policy optimization-based method, is it really bringing us closer to understanding policy optimization style algorithms, or it's answering like a different but still interesting question? I would say that it's a bit of the latter, but maybe you have a different view on this.
I would say that, in my opinion is as follows. I think that eventually, I do have a belief that it's hard. I'm not sure how to answer, because first of all, I would say that just to put it to get it out of the way, this solution, what our paper does, I don't think it helps us in any way understand policy optimization algorithms better. I think it was a solution to a technical problem that we don't experience it in practice in any way, right?
Right.
Especially, we also know that we're using your least squares concentration bounds and doing this uniform convergence because we have this big class of value functions. But we also know that deep learning doesn't even act this way. It's kind of so there is so many differences, and just this is like a technical solution to a technical problem. But from a larger perspective, I would say that maybe eventually, like if we go a step further and study the actor critic type algorithms which learn the Q function by gradient steps, which can also be based on, by the way, I didn't mention, but the papers that do this make the exploration assumptions. They are basically studying an optimization problem. But if you take, for example, a follow-up work that would take this algorithm template and combine it with developing a policy cover or doing this kind of using past samples to estimate value for whatever, then I would say, yeah, maybe I don't see it right now, but I do think that maybe eventually we could draw some insights from theory about how to make these algorithms better. But it's very speculative. I think it's still a kind of a long way to go to get there. But I would guess, yeah.
Yeah. No, I have like very similar thoughts about this as what you outlined, that the issue that this trick is addressing is
completely
a very technical issue,
Yeah.
and we don't even have an idea whether this is a real issue or not, right?
Yeah. Agreed.
Nevertheless, the solution is very cool, and it does help us move around it in a certain way. I'm just wondering if there's any hope of laying this covering number argument to rest and coming up with an alternative to this, because somehow, like, the technicalities that this leads to, it feels so strange and artificial to me that.
Yeah, I agree. I was actually at some point I was looking into doing some kind of a stability argument. So I won't need the uniform. If the estimated value function, when you change just a single state action in the data set, does not change by much. Yeah, like kind of. I hope the intuition is clear. Like same as algorithmic stability. Then you would not need the discovering number, okay? Because but it didn't work. You can make actually this kind of argument work if you don't have a martingale setting. But in the martingale setting, it didn't work. I did. That's one thing I tried that I got to the conclusion that doesn't work. And if it would circumvent the need for a covering for this uniform concentration. But yeah.
So when you say martingale setting, do you mean in contrast to, let's say, like an IID setting, or?
Yeah, in contrast to I forgot the name of it. When you have the independent variables just fixed, and you just sample the dependent variable. The independent variables don't have dependence between them. It's called.
I see. So like a fixed design.
Yeah, fixed design. Yeah, that's what I was looking for. Indeed.
Let's see. That sounds like a curious direction. So, and any idea how to do this in the bandit setting?
So actually, the same technique, of course, works in the bandit setting because it's only again, in terms of not clipping and controlling the value function capacity and all that, it works in the bandit setting, but there you have many other problems. Actually, the work I mentioned, one of the works I mentioned in the beginning already uses this method to get to so the bottom row, the work by Liu et al. In their policy optimization approach, they use the same technique. They use what we did with the warm-up, and this, along with more improvements over previous works, got them to k to the power of 3 over 4. But the challenge that remains in the bandit setting comes from the need to estimate when you're doing the geometric hedge estimator, you need to plug in the second moment matrix of the occupancy of the policy.
Right. Yeah.
And estimating that is the why they get to k to the power of 3 over 4. If you have that given, then it's already then you get to square root k.
Right.
The suboptimality in their algorithm comes from the fact that they use batches to just sample get many samples from this second moment matrix.
Right. Yeah. You need to waste a lot of samples to do that.
Yeah, exactly.
I guess there's another question in the chat. I can just read it. It says that, like, not sure, but in the linear bandit setting, it might have some cool connections with IDS too.
To be honest, I'm not super familiar with information-directed sampling. I know the term, and I've read maybe 1 or 2 papers relating to it, but I'm not.
Like somehow there exists a connection between IDS and mirror descent, but I would say that is or at least it looks quite orthogonal to me, to this application of mirror descent that you do in this paper. I guess if one wants to understand this question a little bit better, then maybe they should be looking at, so maybe that's my recommendation to Ali Reza, who asked this question. Maybe you want to look at those papers that relate the regret of mirror descent to the analysis of IDS. See if there's a way of reconciling that with this analysis.
Yeah, I do have some naive questions. So one of them is about the ergatum. Like in the ergatum, you still have truncation, so to say, or whatever, like this indicator, right?
Yeah.
So what happens if you remove that?
So the problem, if you remove that, the problem is technical because you won't be able, right? What I want to do in the analysis is so I can use in a good way the concentration result. I must argue for a bound on the sup norm of the Q functions. But the problem is that if I'm not doing this clipping, then the Q functions outside of the known state set will be large. So I'm not, you know what, I'm not completely sure. Perhaps there is a way to make the argument work without the clipping, because most of the time you're
not there. Yeah, I was wondering whether you can just like factor out this argument that you had at the beginning that you're not going to those states anyways. So there is that error event, and you separately treat that, and then the ergatum would become much simpler, right? Like, or not much, but like just you can remove this indicator for free.
I tend to agree. I think, you can just apply this inductive argument only for under some event that happens with high probability, and when it's not, I guess.
Okay.
Yeah, I think perhaps you can make it work. I tend to agree. Yeah.
Okay.
Yeah.
We can think about it offline, like both of us. The other question is compute. So we have the pesky bonuses, I guess, and then that prevents us from having a low complexity solution in terms of the policies, right? Like, how long does it take for me to sample from a policy? And for that, I need to sum up all these Q functions that I got so far. And that would be super easy and very nice if they were all linear.
Right.
But they have the nonlinear component. So that's the only thing, because the loss is linear, this p hat business is also linear.
Right.
So those can be summed up, but the bonuses are pesky.
Right. It's true.
So because of that, it's like as time goes by, it becomes more and more expensive. So I was wondering whether you were thinking about somehow, like that seems to be different, like very different from what the policy optimization people would want to do, which is that like you have an explicit policy representation with, like a d-dimensional parameter. And then here we don't really have that.
Right. So we gave it some thought. Also, we had to do something with it, because otherwise it would run into again the covering number issue. So since we put it on a schedule, first of all, it's instead of having a d-dimensional parameter for the policy, like I show here, when you include the bonuses, you have d times log k. Okay, because we only update the policy, the bonuses, logarithmic number of times. But the other thing we tried to make it more elegant is, if you apply, if you don't, because the bonus, let's put it here just one second. The bonus is counteracts exactly this uncertainty here, which is unfortunately this right. It's a square root of the norm induced by the covariate matrix. And this is why you can't, when you sum the bonuses, again, they don't collapse to a single d-dimensional vector. But if you play with A and G, then you can make it squared. And then they do collapse, and you don't care about about epochs and everything. But the problem is that when you do it, you have to multiply, you have to inflate the bonus by a factor that ruins everything in the concentration again. So we really couldn't get out of it, but perhaps there is a way to make it work.
Yeah, I thought it'd be super cool.
Yeah, I agree.
Okay, those were my naive questions.
Maybe I'll stop recording here.